Hey everybody, welcome back. Oops, sorry. What we're going to do in this video is look at what a negative lens can do in terms of image formation. And it turns out by itself, the only thing a negative lens or diverging lens can do is form a virtual image. But before we get to that, let's see how we define the focal length of a diverging or negative lens. So what you see here is a generic shape for a negative lens. Remember, negative or diverging lenses, they're always going to be thinner in the middle. Converging lenses, also known as positive lenses, we've already discussed and said that they're always thicker in the middle. So a diverging lens will always be thinner in the middle. So this hourglass shape is a conventional shape for a diverging lens. But any lens that's thinner in the middle is going to be a diverging or negative lens. So for instance, you can have shapes like this. You might have a lens that looks like this. Curvature, and then more curvature. Okay, so you can see if you trace your fingers from the edge down to the center, right, it's thinner, that lens is thinner in the center. So that also would be a diverging lens. It doesn't have to have this, what I'm saying, calling the hourglass shape necessarily. In fact, we'll look at this in more detail in another video, but if you wear glasses to see things that are far away, you actually have a diverging lens that looks like this one up here. It's thinner in the middle, and your eye is going to be over here, and you're going to be looking at things that are over here. Okay, but again, we'll look at that in another video. But let's see how, again, we determine the focal length of the lens. So what we do is, as you can see right here, again, we send light in a collimated beam, parallel rays, parallel to an optic axis. We send them in from the left traveling to the right, and we ask ourselves what happens to that light. Now, just like with the positive lens, there are really two refractions occurring. You can see for this top ray, this first ray is going to bend towards the normal, but because of the shape of that lens, see the surface normal is like this. So this angle is bigger than this angle. So that light ray gets bent towards the normal, and then there's another refraction at the second surface. And if you look at that surface normal, which will be like that, this ray will bend towards the away from the surface normal. So it'll come out like this. And you can do this with all these other rays. And if you do that, you'll find out that all the rays that leave the lens, they're diverging as they're moving to the right. So what you do is you trace them backwards. So just go straight back from right where they leave the lens, just go straight back. And you'll get these dashed lines if you trace them all backwards. And they all appear to come from this focal point, the so-called front focal point. So that is how you would define or determine the focal length of a diverging lens. You would measure from the center of the lens to this front focal point. Because again, if you send in a beam from the left traveling to the right, the rays diverge as if they came from this front focal point. Now, the reason it's called negative is that sign convention, plus minus sign convention, focal lengths are measured from the center of the lens to the focal point that is, quote, used if you send in the light, a collimated beam from left to right. So for the negative lens, it's this focal point that is, quote, used. So if I would measure the focal length from the center of the lens to that focal point, see that arrow points to the left. So in formulas, I would have to make sure I put in a negative focal length in order for the formulas to work properly. So that's why we call it a negative lens. Okay, there is a back focal point that would be the same distance from the center of the lens. And just like with positive lenses, when you do a ray trace, it's useful to put both of these focal points just for reference. Okay? All right, so that's what we mean by the focal length of a diverging or negative lens. Okay, now let's try the image formation now and see what that looks like. So this shows a ray trace for an object that's right here, out here. Okay, and you can again see, look, here are the two focal points we just talked about. So if we look at this static picture, here's the first ray that I would draw from the tip of the object arrow. It goes parallel to the optic axis. And just like with the positive lenses, in our approximation, right, to take a shortcut, we just have the rays come straight into a single surface at the center and then bend from there. So because this ray is parallel to the optic axis, it's going to diverge as if it came from this front focal point. So when you draw this orange arrow, you have to be careful and make sure that it looks like it's come from that focal point. That's the tricky part when you do this negative lens ray trace. Okay, so there it is right there. The second ray that we draw, ray 2, that goes right through the center of the lens, straight through that intersection point. Remember, I said when we were talking about positive lenses that second ray is always going to be drawn the exact same way. It's going to go straight through the center of the lens, whether the lens is positive or negative. Okay, now that's all you have to do, because if you have those two rays, ray 1 and ray 2, you see as they leave the lens, they're diverging. So what we do is we trace them back. So trace this ray backwards. There you see that dashed line going to that focal point. Now trace ray 2 backwards. Now you don't see the dashed line here, but imagine I'm tracing this ray backwards. And look, it will intersect, tracing that ray backwards, that line will intersect with this dashed line from ray 1, and it intersects right there. That intersection point is the tip of the image arrow. So then what we do is we just draw in that image arrow. Okay? So we now know where the image is located. Ray 3 is not necessary, but if you did draw ray 3, you would find out that when you trace it backwards, it also intersects at that point. But just forget about ray 3. You don't need it. Okay, now, how do we describe this image? Well, it's formed with diverging rays, right? So it's going to be virtual. And to see the image, your eye's going to have to be over here. Okay, so we can label these things, these quantities. There's the focal length from the lens to the front focal point. There's the object distance from object to the lens. That would be positive in this ray trace. The image distance from lens to the image location is Q. That would be negative if we had to pay attention to the plus minus signs, like we were using a formula. Okay, so that would be negative because the image is formed on the same side of the lens. Okay, so that's virtual image formation by a negative lens. Oh, there's the object height H, and there's the image height H prime, and both of those would be positive for this ray trace. Okay, now it turns out, there's your eye to catching some of the diverging rays, and that's how you could see the image. And when we do the thin lens lab, you'll get to see the virtual image formed by a single negative lens. Okay, all right, that ends the show, but I do want to go, that ends this PowerPoint set of slides. I want to go to another applet that does negative lens ray tracing. So I'm going to go to our course page, and I'm going to click right here, negative lens ray trace, because I want to show you guys something with the negative lens. And that is, all right, so look, right here, you see that there's the red object arrow. Look, here's that first ray, this green line, horizontal line, parallel to the optic axis, and it's going to diverge as if it came from this front focal point, that little black dash. The second ray that we draw goes right through the center of the lens. All right, so trace those rays backwards, and that's what you see in yellow here. This ray traced backwards gives you the yellow. This ray traced backwards is right on top of itself, and they appear to come from a common point, which is right there. So you get this tiny little image arrow. And if your eye is on the right side of the lens and catches some of the diverging rays, you're going to see that image right there. Now, watch this. If I change the object distance, I'm going to start bringing the object closer to the lens. You can see that I'm still getting a virtual image. It is getting bigger in height and formed closer to the lens. At the focal point, if I put the object at the focal point, you might recall for the positive lens, if I put the object at the focal point, the rays that leave the lens are parallel, so you don't form an image. That's not the case here. In fact, what will happen is the image distance will be exactly half of the object distance. Now, if I keep bringing the object inside the focal point, I still keep getting virtual image formation. You see that? So I'm always going to be getting a virtual image where the image is formed between the object and the negative lens. For the positive lens, when we brought that object inside the front focal point, we formed a virtual image instead of a real image, right? So that was a definite difference in the image type. But a single negative lens always does the same thing, meaning that it always forms a not inverted or upright virtual image in between the object and the lens. And it is impossible for a single negative lens to form a real image. It just can't do it. Okay, so keep that in mind also. Okay, now I'm going to end the video, and I'll see you in the next video.